Dr. Gary Griggs is going to give a talk about climate change, sea level rise, and coastal retreat. And Dr. Griggs grew up in Southern California, and you're a surfer, weren't you? Yeah, okay. He was a surfer down there, and he eventually attended UCSB in Santa Barbara and went on to do his graduate work at Oregon State University in oceanography. And his favorite ice cream flavor is Jamocha almond fudge. I learned that tonight. And then I really like this. Dr. Griggs has had one career. He's been around the world 2 times. He has 3 grandchildren. He's built 4 houses. He has 5 regular children. And he's written 6 books. So anyway, Dr. Gary Griggs.
The first thing I wanted to say was I'm really impressed on a Friday night to see this many people coming to a talk. If I had this talk in Santa Cruz, there wouldn't be anybody there. So I can only draw 3 conclusions. Either this is a really exciting topic, somebody's giving you extra credit for being here, or Modesto is really a quiet place on Friday night, and this is where it's happening. So normally I use a Mac, and we're on a PC tonight, so I think we've worked everything out, but the topic may not seem necessarily pertinent to you in the sense of coastal retreat, although, does anybody know what the elevation of Stockton is, roughly?
Stockton's like 10, Modesto's about 80.
Maybe 80? Okay. So, I mean, you could have oceanfront property, but that would require melting or breaking up Greenland and part of Antarctica, which isn't going to happen in our lifetime. So, if I showed you an image like this to start with, and then tell you this isn't really going to happen, then you all feel a whole lot better. So I want to start by making you feel a whole lot better. Sort of like giving a student an F and they feel horrible, and you give them a D and they feel really good. So we're going to see how this works here. And I'm just going to start by saying climate change is real. And in a discussion at dinner tonight, a discussion that nobody really questions climate change. That's not really true. There's some other issues around why it's happening. But I'll just start by saying there's a very strong consensus, a lot of evidence that it's happening. In large part, it's due to human activities today. And unless we do some things fairly soon to both mitigate it, meaning to try to reduce it, and to adapt to it, meaning it's happening and there's things we need to do if our society, whether it's agriculture, whether it's where we've developed or our water supplies, to adapt to it, there's going to be some challenges that we're going to have to face, and maybe we're facing those already. So this was an interesting article that came out a little while ago, and it actually references a report put out in 1975 that said global warming was of concern. So 36 years ago, but it's an article about why do we have an allergy, which I think is an interesting way to put it. So where we are today is on a long, sort of slow trajectory of climate change, and a lot of different scientists have used a number of different models to try to project out into the future, because things are very hard to predict, especially the future. Sometimes it'll take you a while to catch on to my sense of humor, but maybe in the course of the evening we'll do that. So using different models for greenhouse gas emissions, for example, we get different values for things like air temperature, ocean temperature, sea level rise, cloud cover, rainfall, and so forth. And there's a lot of uncertainties, things we just don't know. For example, the natural climate variability and how that may fluctuate in the future. The trends of future greenhouse gas emissions. We'll talk a little bit more about that, but we don't know what China's going to do. We don't know what India's going to do. We don't even know what we're going to do. And second, how does the global climate system change with all those? One of my favorite climate scientists had a great quote. There are the known knowns, the known unknowns, and the unknown unknowns. And climate sort of falls into that in some ways. There's some things that keep surprising us, and there's some things that we know about pretty clearly. We knew or have known for a long time that climate varies across the globe. If anybody doesn't understand what I'm saying, I'm going too fast or complicated concepts, just raise your hand or we can try to clear up things, but just don't interrupt me, okay? So we knew there was ice in the polar regions, we knew it was warm in the tropics, but beginning in about the early 1800s, there was a perception that began to grow that not only was climate different across the face of the Earth, but climate had changed over the Earth's history. And one of the early evidence for that came from places like the Midwest and Switzerland and England, things we now call glacial erratics. And these are big chunks of rock that are foreign to anything around them that we'd find on farmlands of the Midwest. And people said, you know, how did those get here? And it turns out, over time, we realized that the Earth had been glaciated, that there were ice ages that had come and gone, and they left pretty clear evidence behind that, for example, rocks had been carried by glaciers from many miles away. So we now know that, say, Seattle was under roughly 3,000 feet of ice at the end of the last ice age. New York City was covered by ice. Most of the Midwest was glaciated. We scoured out the Great Lakes. In fact, we call the glaciations or name them by how far they came. There's the Nebraskan, there's the Kansan, so forth. So we know the Earth looked very different at times in the past. So we've gone, as scientists, back into the past to look for clues to those ice ages, look for clues of temperature change. And one of those has been the ocean drilling program. This began in 1968. It's been going on for 42 years. And by drilling holes into the ocean floor, going down thousands of feet in tens of thousands of feet of water, we've brought back sediment cores going back 100 million years and beyond. And the record of the sediments in those cores tells us something about the temperature of the water. And we can go back and determine how ocean temperatures have changed because the plankton changes and those planktonic shells are deposited in the ocean sediments. And we can go back and look at the chemistry of those shells. We've also gone into the Antarctic and Greenland, and by drilling into the ice, we've gotten records now. Greenland that go back about 110,000 years, and in the Antarctic about 740,000 years. And we can tell from the chemistry of the ice, not only we can find, say, eruptions of volcanic glass or ash that we can date to particular eruptions, but we can also find from the isotopes of oxygen and so forth, what the temperature was like. So these records from Greenland and Antarctica have enabled us to go back 100,000, 750,000 years and look at how temperature has changed way before modern humans evolved. We know there's a number of natural causes of climate change. Those include changes in the amount of energy produced on the sun, volcanic eruptions, even movement of the Earth's tectonic plates, and variations in the Earth's orbit around the sun. A couple of years ago, we were in Nepal and Tibet and Bhutan and flying over the Himalayas, and you can see, in fact, where glaciers were and how they've retreated. And there's lots of images out on the internet now that you can see where glaciers were in 1880 or 1920. And globally, overall, glaciers are retreating as the temperature's gotten warmer. The ice is melting and that water is flowing into the ocean and slowly raising sea level. Solar energy changes over short term. We have sunspot cycles, but those are on the order of about 11 years. So the climate changes we're seeing are on a much different time scale than 11 years. So while these are happening, those aren't the kinds of things that are influencing the changes we're seeing. We also know volcanic eruptions. This was a few years ago in Iceland. A lot of disruption of aircraft traffic leaving Europe. But most major volcanic eruptions, whether it's Krakatoa or Tambora, or this particular one that's very hard to pronounce, last months or maybe a few years, but not tens of years or thousands of years. So these are short-lived, but definitely have significant effects. We also know the Earth's tectonic plates move around. And on a Mac, I could start and stop this. So I can't do that. But when this starts at 250,000 years ago now, we're showing how the movement of plates has created things like, watch India ram into Asia, and what it does, it pushed up the Himalayas. I got to get through that one. It pushed up the Himalayas, which began to have a number of effects. It starts to change atmospheric circulation. That's the Tibetan Plateau is probably the largest, highest landmass that have ever existed. So the movement of plates, opening of ocean basins and closing them has also affected climate, but on a different time scale. The major force that seems to have influenced climate over the history of the Earth, going back since we've had oceans and atmospheres, say 3.5 billion years, has been variations in the Earth's orbit around the sun. We call those the Milankovitch cycles, discovered or kind of worked out by a Yugoslavian, actually was a civil engineer. And there's three that are important to climate and ice ages. One is the Earth's wobble on its axis, which has a cycle of about 26,000 years. A second is the tilt of the Earth on its axis, which gives us the seasons. And that tilt actually changes from 22 to 24 degrees, which has a cycle of about 41,000 years. And then the Earth's orbit around the sun is not circular but elliptical, and that has a cycle of about 100,000 years. So each of those is going on, and those interact in different ways to get us a little further from the sun or a little closer to the sun, which makes the Earth a little warmer or a little cooler. And it's the way those interact over time that can bring on ice ages and other climate changes. But these, again, are over thousands of years. Those are very long cycles. Whoops. So if we go back over time, and this just goes back 1,000 years, we can reconstruct global temperature. And this is northern hemisphere. I'm not going to show a whole lot of complicated plots, but this is just showing sort of 0 is a period that we average the temperature over about a 1960 to 1990. We looked at that as sort of average. And then we looked at the period before that, and this is from ice cores, for example, and found that it was considerably below that. And there's a lot of spread in the data, but this is sort of a running average. So you can see it's been colder than the modern. And red are actually instrument records. So what we've seen over roughly the last 100, 110, 120 years is the Earth relative to the last 1,000 years is getting warmer. So it's not happening on a scale of thousands of years or tens of thousands of years, but it's happening over hundreds of years. So climate is changing faster than it has in the recent historic past. And everybody, I think, is quite familiar with the greenhouse effect. You can also call this the roll up the windows in your car effect. It's not the thing you want to do to your dog or your child. But essentially, a greenhouse and the Earth's atmosphere do the same thing. The content of the atmosphere, actually we have a natural greenhouse effect, so the Earth is warmer than it would be otherwise, which makes the Earth habitable. But we get shortwave radiation coming in through the glass of your car or your house, just like shortwave radiation comes in through the atmosphere. It heats up the greenhouse, or it heats up the seat of your car or your dashboard or your steering wheel, and it re-emits long wave back radiation. That cannot get out through the glass, so your car gets very hot, and it cannot get out as easily through the greenhouse gases. So that to the degree that we're changing the composition of the atmosphere, we're trapping more heat. Sort of like putting on another blanket that we can't easily take off. So these are what we call the greenhouse gases, and the one we hear the most about is carbon dioxide, which comes from burning of coal and gas and oil. Methane, which comes from leakage from things like vegetation, from permafrost thawing. Cattle actually burp and produce a lot of methane, which What are you going to do about that, you know? And rice production produces a lot of methane. Nitrous oxide comes from industrial process, also burning of fossil fuels. And then we've got ozone and chlorofluorocarbons. These are from refrigerants that we've pretty much phased out. But each of these, we can see how much they've increased since the Industrial Revolution, basically. Carbon dioxide's gone up about 40% in the atmosphere from what it used to be. Methane has gone up over 100%. These did not exist before, so it's gone from 0 to 10 to 80 parts per billion. These sound really small, but they have a big effect. These are the relative contributions. So if greenhouse gases total 100%, carbon dioxide is the biggest one. Methane is most of the rest, and these all have a contribution. And these are their ability to absorb heat relative to carbon dioxide. So methane absorbs per amount of methane released from those cattle burping 25 times as much heat as a CO2 molecule. And some of these are much, much higher. So far, they're not as important because the concentrations aren't as high. But what it tells us is there are potential problems ahead if those numbers get a lot larger. So as the Earth has, or the Earth's atmosphere has warmed and cooled over time as we've gotten more or less solar radiation. Earth has warmed and cooled. Glaciers and ice caps have advanced and retreated. And when we melt that ice, we raise sea level, or when we transfer water from the oceans to the ice caps and the glaciers, we have to lower sea level. There's a lot of these pictures around. This happens to be Mount Hood in Oregon over about a 20-year period, both at the end of the summer. And you can say, well, some of those pictures, we took them in a good year, bad year. You can look at Kilimanjaro and lots of other glaciers and see, in fact, that the snow cap, the ice in the Arctic is all diminishing or retreating. And what that did was change sea level. So by convention today, we say where sea level is 0. But if we go back, this is just the elevation of sea level compared to today, 40 meters below the present, or below 0, 80 meters, 120. So say almost 400 feet below present. And this is going back in time. So this would be 100,000 years ago, or 50,000 years ago, 200,000 years ago, 300,000. So a lot of this has come from ice cores. But what we know is, as the climate has changed, sea level has changed. So during the peak of the Ice Age, so we have one more image in here. This is where it is today. We transferred about 11 million cubic miles of seawater to the continents as ice and glaciers. So sea level had to be lowered about 350 to 400 feet. So if we go back about 120,000 years ago, 130,000 years ago, sea level was almost 400 feet below where it is today. As it warmed up, sea level rose fairly quickly. So these oscillations are part of those, what we call the Milankovitch cycles, the 20,000, 46, 100,000 year cycles. Sea level's been 20 or so feet higher than today. But here where it is today, if civilization had evolved 10,000 years ago, all those cities would be under 150 feet of water today. And there is one set of archaeologists, anthropologists that believe that the reason civilization advanced when it did, beginning 3,000 or 4,000 years ago, was because finally sea level stabilized and the deltas and the coastal plains of the world could finally be used for permanent agriculture. So civilization may have had a lot to do, its advancement, with what sea level has done. But this is the change over the last 350,000 years. So we transferred a lot of water from the oceans to the continents. That lowered sea level by roughly 350 feet. Whoops. How has that affected the coastlines of the world? How has that affected the shorelines? You can imagine if you drop sea level or raise sea level that much, coastlines are going to change. And we look today, at a satellite view of the Earth at night, it's amazing how densely populated the coastal regions are. And globally, about a third of the people now live in what we call coastal areas, within an hour, within 50 miles of the coast. Even places that we might think of as not very densely populated, the coastlines can almost all be delineated by lights at night, particularly the Mediterranean, the US, Japan, China, and so forth. So most of the world's people live relatively close to the ocean and relatively close to sea level. If we look at the mouth of the Golden Gate in San Francisco, these are the Farallones. So this is about the outer edge of the continental shelf, 110 meters or so. This is where sea level was at the end of the last ice age. So we could have, walked out to the Farallones for lunch. So in the intervening period of time, sea level has risen roughly 350 feet. The shoreline has retreated at about 7.5 feet per year. So the coastline used to be here, now it's right at the Golden Gate. Because there's a lot of people living close to sea level, the present estimates are about 150 million people living within 3 feet of sea level. And you can imagine where those are. People in places like Bangladesh, Santa Cruz, Los Angeles. Most of the world's cities are on the coast. So this happens to be Santa Cruz, the boardwalk. This happens to be Rio de Janeiro, and you think those are crowded. This is China. When 1.3 billion people get hot and go to the beach all at once, it's hard to find a place in the water. So one of the things we're thinking a lot about now is what sea level will do in the future. And this is trying to get a little bit of historical perspective. So this is going back to the year 1800 up to about 1900. And sea level at that time, most of our numbers are from geological estimates. Again, whether it's ice cores or whether it's organisms that might have lived along the coastline that are now buried, former beaches. Tide gauges around the world began to be installed back in the late 1800s. So this is the trend from tide gauges that show not only the tide going up and down, but how sea level is increasing. And those numbers for the last century are about 1.7 millimeters per year globally, about 8 inches in a century. Nothing really to be worried too much about. Beginning in 1993, we started using satellites, which are better in the sense that, first, it's a marvel to me that we can use a satellite or use a series of satellites to get the elevation of the sea surface. But then I don't understand cell phones either, so. The problem with a lot of tide gauges is that the land moves also. So we can put a tide gauge in San Francisco or Eureka or Astoria or London, and if the land is rising or sinking, then that tide gauge will read something different. So for example, in Juneau, Alaska, Alaska's rising. Ice was removed. The glaciers depressed Alaska. As the ice is melted, Juneau is actually rising. So relative to sea level, Juneau is going up faster than sea level is. They're not worried about sea level rise in Alaska. They're worried about permafrost thawing. New Orleans, on the other hand, is sinking because of the huge mass of the sediments from the Mississippi Delta. So its sea level rise rate is almost 10 times this fast because the land is sinking as sea level is rising. So tide gauges have some inherent problems. We have to average them, but satellites are getting that very accurately. And from the last roughly 93, 18 or so years, the numbers look like they've gone up, almost doubled the global rate of sea level rise. So where do we go from here? I'm on a national committee now of the National Academy of Science, and we've been asked by the governors of California, Oregon, and Washington, as well as federal agencies, to come up with a range of numbers for sea level rise by 2030, 2050, and 2100. You might say, well, why would you worry about that? And it's because we have billions of dollars in investment in the coastal zone. Development, private development, sewage treatment plants, outfalls, freeways, parking lots, parks, hotels, restaurants, harbors, ports. So these make a big difference, and we need to start planning for that. So there's a couple of ways to do that. One are models. We model everything today. Kind of trying to project out into the future where we look at all the inputs and say, well, if we have this much greenhouse gas emission, that'll melt the ice this fast, that'll warm the ocean this fast, and that'll expand it. These are the ranges we might expect. There's also been some empirical reasoning where we actually compare the Earth's temperature to sea level, and we try to get a more direct relationship without worrying about a model and all the components of it. We say when it's this warm, globally, the ocean's temperature is this warm, that means it's expanded this much ice will melt. And these numbers now out to 2100, which we won't have to worry about, go from roughly 14 inches to 4.5 feet. So those are some of the ranges we're worrying about. But again, we model all kinds of things. We project all kinds of things. I think if you're a parent, you start to project or model how much money you need for your college education of your kids. Gee, there's going to be some inflation. College is going to cost more. Is it going to cost $10,000 or $50,000 or $100,000? We better start saving. So we do that in our day-to-day lives. Retirement. Do I need this amount or that amount? And then what happens if the stock market goes? Where's my money going to go? So we are always looking out into the future. And this is another example of that. So lots of impacts depending on where we are. The lower we are in elevation or the closer we are to sea level, the more we're going to feel those effects not only now, but in the future. This happens to be Bangladesh, and this is just a fairly simple pattern that shows Bangladesh today has a total population of 112 million people, the land area. If we raise sea level 1.5 meters, say 4.5 to 5 feet, because this area is so low, it's basically the delta of the Ganges, we would affect 17 million people, about 15% of the population, and they would basically lose about 16% of the land area. So those 17 million people have to go somewhere. And if we look at Bangladesh today, there are millions of people living on these muddy islands in the Ganges that during a cyclone or a typhoon will go underwater. There have been events in the last 20 or 30 years where 100 or 200,000 people will die from a major storm because they're living so close to sea level. So they have some very real problems. There's a number of South Pacific islands and Indian Ocean islands that have been talked about. A lot of publicity because, and this is one in the South Pacific, Tuvalu, where the average elevation is about 4 to 6 feet. So during a very high tide or a storm, they can go underwater. These are kids sitting on their front porch during a high tide. We don't have to worry about that here in Modesto, but there are places in Santa Cruz, Capitola, where during a really high tide, some of the restaurants do get flooded. Venice has been sinking for a long time for a number of reasons. Partly it's groundwater withdrawal. Partly it's like New Orleans. It's a delta that's sinking. A lot of important artwork and buildings. I don't know if this is real or not. We can do amazing things with Photoshop. I want to think it is real. It's possible. I'm just not sure what's pulling this guy on his wakeboard, but it's one of the side effects of flooding Venice. Somebody's taking advantage of that. And then Florida, one of the things that's very obvious when you start looking at coastlines, which is where most of my work has been focused. If you've ever been along the coast of Florida, Georgia, the Carolinas, Virginia, it's a totally different coastline than the West Coast. If you've been down the coast of Big Sur, and then you go along the coast of Florida, you say, where are the mountains? There aren't any mountains in Florida. Highest elevation in Florida, I think, is at Epcot or Disney World. I think it's the fake Matterhorn. It's like 300 feet. Most of the Carolinas, the coastal plain is very flat and very low. So these are the parts of Florida that are only a meter above sea level, and that's about the mid-range of where we think sea level might be in 2100. And if you stop and think about what's out here in places like Miami, we have a lot of stuff very close to sea level. And that raises a lot of questions. You know, well, can you move Miami? Let's not believe those numbers. And Miami gets damaged now from hurricanes, which is separate than sea level rise. It raises sea level very quickly on the order of meters. So there's not only this long, low ramp of sea level rise, but then we have these short-term events as well. And we've got a lot of East Coast areas. Again, there's no rocks, there's no cliffs. It's all very low sand. This is actually up near Martha's Vineyard, Cape Cod. But we've got, I don't know, this is almost like something somebody in Santa Cruz would do. We don't have a coast that looks like that. So we have a different sort of a coastline with houses that are being undercut, that are ending up offshore. So these are ongoing problems we've had for a long time, but as we go into the future, we'll see these kinds of events probably happening more frequently and more severely. A lot of the Southern California coastline is very densely populated, and it's been built right down to sea level. Whether it's Long Beach, Redondo Beach, Hermosa Beach, a lot of those beach towns are built right down on the water's edge. And the next picture is taken right here. This looks very safe. There's actually a little concrete wall along here to hold back sea level. This is the time when most of these people sell their houses. They look great in the summer months. The next picture is taken during a high tide and a set of storm waves in late 1988. This is Mission Beach in San Diego. And you'll notice somebody standing right here and then some other people standing in front of this house. So it looked like a totally different place. So this is the house. There's the one with the tile roof. And you say, my God, what happened to the beach? So these are short-term extreme events, typically elevated sea levels from very high tides combined with storm waves without any sea level rise. So those two are going to become additive. This happens now. Some indication that waves are getting larger, storms may be getting more frequent. But if we add a foot to high tide, or 2 feet, or 3 feet, or 4 feet, you can imagine instead of happening every 10 years, it's going to happen every year. And those are some of the concerns that people have about the future. I'll just put that in there for a little humor. Maybe that's not funny if you have a beach house. One of the areas that has become of considerable concern, by and large, probably for the next 50 years, sea level rise itself isn't going to be the biggest problem in most places. So those graphs I showed you of how high sea level might get, we can pick an average number. Maybe by 2050 it'll be 10 inches higher or 12 inches or something like that. It's going to be the waves and the storms on top of that. However, around San Francisco Bay, most of the development was built on fill. The San Francisco Airport, Candlestick Park, the Oakland International Airport, Alameda Naval Air Station, Foster City, Redwood Shores, were all built on fill 20, 30, 40 years ago. At that time, we brought in a lot of earth. Some of it was on garbage. And we got these structures a foot or so above high tide. Why bring in any more stuff and make it even higher? It's going to be much more expensive. So they got it up above high tide and said, fine. So we've done some measurements recently, taking the average monthly high tide and adding 16 inches, which is one of the sort of moderate to high estimates by 2050, only 38 years away. And this is the San Francisco Airport. This is 101 in blue with just 16 inches of sea level rise. So the airport is not very high. And you can say, well, that's okay, I'll use the Oakland Airport. The Oakland Airport looks exactly the same. So overall, I would say most pilots don't like to land in the water. So this isn't a trivial problem. I mean, it's a huge airport. Probably all have flown in and out of there many times. What do you do? Do you build a wall? Do you build a levee around it? How high do you make the levee? And what about the areas around it? So these are not easy problems to resolve. If we look at the tide gauge for San Francisco, and actually it goes back to almost the gold rush, about 1850. This is an instrument set out right under the Golden Gate at a place called Fort Point. And essentially what it does is just records water level. It filters out the waves, but it records what the water level is at that station over time. So this is 1900 all the way up to, this stops at about 2000. But this is the overall rise at about 2.1 millimeters per year. A little higher than the global average. That'd probably be 10 inches in a century. But if you look on top of this are these little blips. And these are major El Nino events. So during an El Nino event, the water is warmer, it expands, and there's this wave from the equatorial region, because an El Nino happens when the trade winds in the Pacific die down, and this bulge of warm water that normally gets moved across to the western Pacific towards Indonesia and the Philippines and so forth, moves back, hits the coast of South America, moves north and south, shuts down the upwelling and the plankton and the fisheries, moves up the coast of Mexico, California, Oregon. So this is one of the bigger ones in 1997-98. So sea level was raised a little over a foot for 2 or 3 weeks. 1982-83 was another one, about 12 inches, and you can see these back in time. So the point is, if we project this out into the future, even if it didn't get any, the rate didn't increase, although now we think it's about 3.2 millimeters per year, you can see it's going to take quite a bit of time before, at 2 millimeters a year, it rises 330 millimeters. So these short-term events are going to be more important in the immediate future. These are things we've seen, they've happened, they've created damage, but those events are going to be on top of this rising sea level. So these are things we've measured, we've documented in the past. How many people have ever been to Santa Cruz? Oh, wow. Lucky guys. It's the only reason I came over here tonight was to get out of Santa Cruz. So Santa Cruz is a very active beach town, and one of the things we noticed is this beach, which brings 3 or so million tourists every year. But what happens as sea level rises to Santa Cruz? Well, there's concrete wall along here, so sea level can't go inland any further. In fact, there are times now during big winters that the water comes all the way up to Beach Street and covers the beach with debris. So these are the kind of events we'll probably see happening more frequently as sea level continues to rise and the storm wave climate probably gets worse. And as you know, a lot of California's economy, coastal economy, is based on tourism and recreation. Most people go to the beach. That's where they spend their money. So this has some potentially very large economic impacts. This is Capitola. Have you ever been to Capitola? Not so much. There's no boardwalk there, but it's kind of a cool little place. Summer of Capitola. A nice beach, not as big. The next picture is taken from right here during the 1982-83 El Nino. And although there's a concrete wall here, the waves came over that wall and into downtown. So these are restaurants. This is seawater. Logs and debris went over that low seawall. So the restaurants have been flooded even under normal conditions today in the winter. Capitola's right at sea level. So anything we add onto the present sea level rise, or anything we do in the sense of increasing the size of waves, will impact Capitola more in the future. In addition to the beaches, the cliffs are also eroding on a regular ongoing basis. Some of you may know Wilder Ranch, just north of Santa Cruz. This was taken about 1890. This was taken 2006. It's gone. Probably many of you have been to Natural Bridges. This was taken in 1890. We can just make that go away. Up to 1970, there were 3 arches, then there's 2 arches, and if you look today, there's 1 arch. So it actually is Natural Bridge State Park, but they still call it natural bridges. So the coastline is also retreating, and it's okay at a park, but if it's under your house, that might be a different problem. Steamer Lane or Lighthouse Point used to have a really nice arch in the late 1800s. It collapsed and left this sort of pedestal here, and if you look at it today, there's a little base of it left, but the coast is retreating, although we put a lot of rocks in there to try to keep that from going any further. So what does that mean for coastal communities and homeowners? Well, I used to see cartoons like this and say that was an exaggeration. This is exactly what's happening here. This is just north of Half Moon Bay. Actually, from this location, you could look out and see the surf break at Mavericks. It's a place called Moss Beach. Well, although there are houses here, the development doesn't really matter to the ocean. Pacific Ocean is 10,000 miles wide. It doesn't care about a few feet on either side. It's going to sort of slosh around. So if you look at that house now, it's gone. This is the foundation. And that's being played out across the coast of California. One of the things you might notice, and you don't have to have a mind like a steel trap to figure this out, this does not look stable. There's no vegetation, it's sliding, it's slumping. So those areas of instability are usually evident, not always. Pacifica, south of San Francisco. If you were a geologist, you might call this material quaternary alluvium or marine terrace deposits, but we can call it dirt. It's not rock, it's not granite, it's not bedrock, it's very weak. So if the beach disappears during a high tide in a set of stormwaves, this erodes fairly quickly. So here was a row of houses built almost on the edge. After the '83 winter, they were all threatened, they lost their decks. They built a rock revetment that was supposed to protect this until the 97-98 El Nino came. The rock revetment crumbled, the waves continued to undercut the houses, and ultimately we lost that whole row of houses, and the rock revetment no longer was protecting them. So Pacific in some ways is sort of a poster child. This is just up coast in 2003. This is 2010. I was just there a year and a half ago. Somebody just bought this apartment unit. They're trying to build another rock revetment here and trying to sort of stick the cliff together. They made them evacuate the building. And now you can buy this. Ocean view, 180-degree view. But there's a whole row of these that are sort of sitting on the edge. And again, this cliff, this bluff does not look very stable. So these are the kinds of problem areas we have. Can we really protect it? What they've done here is build something called a soil nail wall where you bore back in and try to concrete that together. I haven't been back for a while, but I think there's going to be some serious problems. And I doubt whether they're going to let people live in those. This is another one in Capitola, just south of Santa Cruz. These apartment buildings were all undercut during the Loma Prieta earthquake in 1989. And ultimately, these are all demolished. There used to be a house here that's been moved back. In fact, this road used to go all the way along the top of the bluff, and on the ocean side of it, it's now gone, there used to be a place called Lover's Lane with benches where lovers could sit, hold hands and stuff. There were trees and a pathway. This is all gone. It's back to here. So it's going back at about a foot per year on a very regular basis. Anybody that's thinking about going to UC Santa Barbara or sending your kids there? This is student housing. And the next picture will show this same area. It'll show this 2 years later, and you'll notice these decks as well. So that one's gone, and you can see the remains of these concrete caissons that held up the deck. So Isla Vista is retreating. And if you know the way college students behave on weekends, it might not be the safest place to live. But they're all for rent. So one of the solutions is relocation. You can move structures back. That's not always popular if you have an oceanfront house. Why should I give that up? This is on the Outer Banks, North Carolina, a place called Redance. and they actually made a movie with this house, Knights of Rodanthe, with Richard Gere or somebody. I don't know, is he a movie star? Richard Gere? Anyway, but the house is going under, so what did they do? They picked it up and moved it down the road. Normally you wouldn't want to move a house quite that size and shape, but house movers can do amazing things. So we relocated to a new place. That's one solution. Another more common in California is we build walls of every sort imaginable: rock, steel, timber, concrete. This is Southern California, northern San Diego County. This is not something most people want to see. Coastal Commission is becoming increasingly hesitant to let people build these, but a third of the coast of Southern California is now covered with some kind of armor. This is the development in northern Monterey Bay, very close to the cement ship in Aptos. And when they built this, they actually bulldozed a pile of sand out onto the beach, and they built a rock revetment along the front of it that was going to absorb the wave energy. It's going to protect them from wave attack. And this would happen during the '83 El Nino. That pile of rocks became a ramp. It didn't absorb the wave energy. The waves went right through the front of that whole row of houses. And when the storm was over, the front windows were blown out. Some of the houses collapsed. Sliding glass windows do not present a lot of resistance to wave attack, but have a good view. And when it was over, they then built a, you see they're still repairing these. This is a wall today that would cost about $5,000 a foot. It was paid for by insurance. Your insurance. It's just the way insurance works. Pajaro Dunes, building on the dunes is never a good idea. This is in southern Santa Cruz County near the Pajaro River, where these beautiful architectural structures were built on the dunes, again during high tides and storm waves without added high tide. They were eroded back, a number of the foundations were undercut, and they then put in about $5 million worth of rock to cover that dune frontage. A little further south in Monterey, there's a series of condominiums that were built right on the edge. Actually, they were back a bit, but this has been eroding back at about a foot or two per year. Apartments were threatened. They put in deep concrete caissons. That wasn't supporting it, so they then built a wall that was supposed to look like an eroded sand dune. So they're becoming a peninsula, and immediately to the north of that is a hotel. It's got a similar problem that's out on the beach, and it's also becoming a peninsula over time, which leads to loss of access to the public and so forth. So these are some of the problems that we are seeing and experiencing under present conditions. So what happens next, we don't know. All of the models are for an increase. That's what we're seeing today. The question is how high and how fast. The other thing that's important is that curve doesn't stop at 2100. It keeps going. We have a lot more ice that we could melt. One of the things that's driving that, I'll finish this up with, is the fact that we're still producing a lot of greenhouse gases. This is just total carbon dioxide emissions. And even though we think we're doing better with renewable energy, the curves are still going up globally. People are still using a lot of fossil fuels. In fact, about 87% of all of our energy globally and in the US is still produced by oil, burning oil, gas, and coal. Hydro is definitely renewable, but the others we think about today are less than 1%. So we still have a long ways to go. We're making a little bit of progress. I will say that is not sustainable, in part because we don't have all that many fossil fuels left. It's an interesting relationship between our carbon emissions per person and our gross domestic product. In other words, the wealthier the country is, as you might expect, the more carbon we emit. I'm not trying to make you feel guilty. I'm sure you walked here tonight. Some of you walked here tonight. So I don't have to tell you, there's a lot of stuff we do today that uses a lot of fossil fuels. We have in the US about 4.5% of the world's population. We use about 25% of the energy, and we have about 25% of the total vehicles. In the hour we're sitting here tonight, in the world we will have gone through about 150 million gallons of oil, 15 billion cubic feet of natural gas, and almost 1 million tons of coal. And as some people have said, there's still a lot of oil and gas out there. We're either drilling deeper into the Gulf, we're going into the Arctic, so there are costs of that, or we're importing it from the Middle East, Nigeria, Libya, Iraq, Iran, Kuwait. But we didn't end the Stone Age because we ran out of stones. We figured out better ways to do things. And I think that's sort of where we are today. But as long as the climate continues to warm, seawater will expand, ice will melt, and the oceans will continue to rise. How do we respond to that? The President's science advisor, a guy named John Holden, says we basically have 3 choices. I mean, we all do. We can either mitigate, we can try to reduce our use of fossil fuels and reduce greenhouse gas emissions. We can adapt to it. We can raise our structures, move back from the ocean, move our crops, move our vineyards, move our cattle to places where the climate's better, or we can suffer. We're going to do some of each. The only question is what the mix is going to be. The more mitigation, the less adaptation, and the less suffering. Personally, I'd rather reduce the suffering. So California's coastlines, which we're not worried about here tonight, have some challenges. We've got more people in development moving one way, and we've got climate change, rising sea level, El Nino, tsunamis, hurricanes moving the other way. These are people in Malibu. I don't feel sorry for them. So I'm just going to leave you with one final image and 2 questions. Is our present use of energy sustainable? And are there tipping points where we go past a certain point and then we have no real way of getting back again? Thanks very much.